Surface and subsurface runoff. What is runoff? The portion of rainfall, snowmelt, and/or irrigation water that runs over the soil surface toward the stream rather than infiltrating into the soil, sometimes called surface runoff. Runoff is sometimes used to refer to both surface overland flow and subsurface runoff interflow. What are the differences between the two? Number 1, surface runoff is a water from rain, snow melting, and other sources that flows over the land surface and is a major component of the water cycle. There are two types of surface runoff that occur during rainfall or snow melt: infiltration excess overland flow and saturation excess overland flow. Number 2 is interflow, also known as subsurface runoff, rapid flow towards the stream channel that occurs below the surface. It occurs below the surface more rapidly occurs than base flow, but typically more slowly than the surface runoff. Rainfall runoff processes. Runoff generation mechanism. When water surface input exceeds infiltration capacity, the excess water becomes infiltration excess runoff. Note that infiltration capacity typically declines during a storm due to the pores in the soil being filled with water, which reduces the capillary forces drawing water to pores. Due to spatial variability of the soil properties affecting infiltration capacity and spatial variability of surface water inputs, infiltration excess runoff does not necessarily occur over whole drainage basin during a storm or surface water input event. Overflow can occur due to surface water input on areas that are already saturated. Saturation from below can also occur when subsurface flow lines converge into slope concavities, hill slopes, hollows, and water arrives faster that it can be transmitted downslope as subsurface flow. Layering in soil can also result in occurrence of the purge water table with subsurface flow above and impeding layer contributing to storm flow. The main processes involved in runoff generation, showing the interaction between infiltration excess and saturation excess and groundwater flow pathways. Most rainfall runoff models are organized around a representation involving partition of surface water input into infiltration or overland flow, either due to infiltration excess or saturation excess. Infiltrated water enters the soil regolith, where it contributes to overflow, percolates to deeper groundwater, or it evaporated or transpired back to the atmosphere. The quantity of water in the soil affects the variety source area involved in the generation of saturation overland flow. The deeper groundwater contributes to base flow and affects interflow through groundwater rise. The stage-discharge relationship. The relationship between the amount of water flowing at the given point in a river or a stream, usually in gauging stations, and corresponding stage is known as discharge, repetition, and rating curve. Study the diagram. The characteristics of the stage-discharge relationship depend on the cross-section geometry, namely shape, size, and slope, and channel roughness, as well as by the physical features of river downstream of the gauge site, which define the type of station control. Station controls can be classified in various ways, which as section and channel controls, natural and artificial controls, and permanent and shifting controls. Flood prediction. Kindly pause the video to study the flood prediction process. Graph analysis. Unit hydrograph analysis The fundamental assumptions implicit in the use of unit hydrographs for modeling hydrologic systems are: watersheds respond as linear systems. On one hand, this implies that the proportionality principles applies so that the effective rainfall intensitizes volumes of different magnitude process watershed responses that are scaled accordingly. On the other hand, it implies that the superposition principle applies so that the responses of several different storms can be superimposed to obtain the composite response of the catchment. The effective rainfall intensity is uniformly distributed over entire river basin. The rainfall excess of the constant intensity throughout the rainfall duration. The duration of the direct runoff hydrograph, this is its time base, is independent to the effective rainfall intensity and depends on the effective rainfall duration. When the effective rainfall is given as a hydrograph, that is, as a sequence of m rainfall pulses of the same duration, the corresponding direct runoff hydrograph can be expressed as a discrete convolution of the rainfall hydrograph unit and the unit hydrograph as. Hydrograph components. Total stream flow during the precipitation during events include the base flow existing the basin prior to the storm and runoff due to given storm precipitation. Total stream flow hydrographs are usually conceptualized as being composed of a direct runoff, which is composed of contributions from surface runoff and quick interflow. Unit hydrograph analysis refers to direct runoff. Base flow, which is composed of contributions from delayed interflow and groundwater runoff. Unit hydrograph theory. It is a typical hydrograph of direct runoff which gets generated from 1 centimeter to an effective rainfall falling at a uniform rate over entire drainage basin uniformly during a specific duration. Effective rainfall is the portion of rainfall which fully contributes towards direct runoff. Therefore, unit hydrograph can be also defined as the hydrograph of the drainage basin which gives 1 centimeter of direct runoff from a rainstorm of specific duration. Advantages. Flood hydrograph can be calculated with the help of very short record of data. In addition, to peak flow unit hydrograph also gives total volume of runoff and its time distribution. The unit hydrograph procedure can be computerized easily to facilitate calculations.